Let's find the area between two curves that cross. Now, in order for us to make sense of this, I wanted to draw a picture for you. So let me draw a y-axis here. Let me draw an x-axis over here. Let me label 3 points along the x-axis. So here's A, here's B. That's going to be our region of integration. Let's put C be the point that the curves cross. So I'm going to have one function look like this. Like this. Let's have a second function that looks like this. Like this. And let me clearly indicate my regions of integration. So we're going to integrate from A to B like this. Okay. My blue function here would be y is equal to f of x. And, this is still f of x down here at the bottom. Y equal to f of x there. My g of x is going to be the green curve. Y equal to g of x. And it's still y equal to g of x over here. And I'm trying to find the area in between these two curves. Okay? So according to theorem, it says, let f and g be continuous functions over some interval a, b. So I have exactly this situation right here. Let R denote the region between the graphs of f and g. So in this picture, you can see that R actually encompasses two regions right here. And it's bounded on the left and the right by these vertical lines, x equal to a and x equal to b, respectively. So the question becomes, how do I find the area R? So if I want to indicate the area R, this is R here, and this is R here, right? So how do I calculate that area? Well, the problem is that the role of the top function and the bottom function changes within the interval. So the role of the top and bottom functions change within the interval. Okay, so how do we fix that problem? Well, I'm going to tell you that right now. The area between the two curves that cross is going to be given by the following formula. Before, we saw that this was just the integral from a to b f of x minus g of x dx. But when we wrote that earlier, that was with the assumption that this f was always bigger than g. When we look at this picture, we can see that partway through, the role of the top function changes, and the top function actually becomes the bottom function. So the way we get around this problem is we're just going to take absolute value of the integrand. Okay? So when you do that, what do you notice? Well, when you look at this function, this area on the left over here, this is positive area, right? But when you look at the area on the right side over here, this area is actually, it looks like a negative area if I didn't put the absolute value. And the reason why is because the f function is actually on the bottom. So if you had something that was beneath the second curve, then this red area over here would be negative. So how do I turn that negative area into positive area? I simply put absolute value there. So how would you actually go about calculating this area? Well, If you actually wanted to calculate this area, it would look like this. You would have your integral from a to b of the absolute value of f of x minus g of x dx. That absolute value is around the integrand. What you would do is you would actually split it up into two pieces. And the place that you're going to split it is you're going to split it at that crossing point C. So we're going to get from A to C, and then we're going to add the result that we get when we integrate from C to B. And for the first integral, the top function is played by f of x. So this will just be f of x minus g of x dx. And for the second part, that's when we really need that absolute value part, because this area is going to be negative, and we know that when you get a negative answer and you have absolute value, you're going to multiply by -1, right? So multiplying f minus g by -1 is going to give you g of x minus f of x dx. So this whole bottom equation is basically how we are going to calculate the area between two curves that cross. And all you see is that we always ensure that the bigger function is on the left side of the subtraction. So for this part of the curve, the blue part's the bigger graph, so the f is in front. For this part of the curve, the green graph is bigger, so the g of x is going to be in front. Why don't we take a look at an example? Let's take a look at example 3 over here. If R is the region bounded between the graphs f of x equal to sine of x and g of x equal to cosine of x over this interval from 0 to pi, let's find the area of the region R. So I'm going to pause this video for a second and draw a graph of the situation. Okay, so all I've done so far is I've graphed a set of axes. Let me graph sine of x in blue. So we know that sine of 0 is 0, sine of pi over 2 is 1, and sine of pi is 0. So this curve kind of looks like this. It kind of comes up like this. Sine of x looks something like that. I'm going to draw, so this is y is equal to sine of x. I am going to draw a graph of cosine of x in green. And cosine of x is, cosine of 0 is 1, cosine of pi over 2 is 0, and cosine of pi is -1. So when I go to graph this guy kind of looks like this. It kind of comes like this, and then it decreases to pi over 2, to 0, sorry, and then it's going to come down like this, okay? So I think after you've drawn the graph, maybe drawing the graph would be step 1. For step 2, you want to find the intersection point. This is the C that I mentioned earlier. That C is the crossing point. So we want to sort of see, what is this guy right here? Okay. And the way that I figure that out is I set the two graphs equal to each other. So I'm going to have sine of x equal to cosine of x. And that's really setting my f of x equal to g of x. And what I could do next is I can divide both sides by cosine of x. So I'm going to have sine of x over cosine of x is equal to 1. And that really gives me tangent of x equal to 1. But we're on this interval from 0 to pi over 2. So tangent of x is going to be equal to 1 at the point x equal to pi over 4. So I could come and I could label this intersection point as pi over 4 like this. All right. Now my goal is I want to calculate the area between these two curves. So I know I need to take my integral and I need to split it into two pieces. So I guess the third thing we'll do is we'll set up our integral. Okay. So I'm going to first integrate from 0 to pi over 4. And on that piece, the green graph of g of x equal to cosine of x is bigger. So that's going to be cosine of x minus sine of x dx. And that's going to calculate the area of this part right here. Okay. Now, for the second area, I need to subtract them in a different order. So from pi over 4 to pi, this time the blue graph is on top. I hope you can see that right here, right? The blue graph is above the green graph over here. So my integral is going to become sine of x minus cosine of x dx, okay? And that's really calculating this red area over here. So all of this red area, this is what the second integral is calculating. Okay. And now all we got to do is take the antiderivative and plug in the points. So I'm just going to write that down. Take antiderivative and plug in endpoints. Okay. So I guess we're not really finding the area. Let me just modify this question to be set up the integral to, if we just put all that right in front of this, then we finish the problem. All right, everyone. We'll work on more examples in class together. Take care.